Well, okay, let's get started. We need to discuss today the ISO standard 18434, condition monitoring and diagnostics of machines, which is an introduction to thermographic requirements on an international standard. So let's get started. Most of you are familiar with ISO, the International Organization for Standardization. It is a worldwide federation of national standards bodies, the ISO member bodies. The work of preparing international standards is normally carried out through the ISO technical committees. Each member body interested in a subject for which a technical committee has been established has the right to be present in that committee. International organizations, governmental and non-governmental, in liaison with ISO, also take part in the work itself of setting these standards. The ISO collaborates solely with the closely with the International Electrotechnical Commission in all matters of electrotechnical standardization. That's quite a mouthful. The Thermographer's Guide, this particular standard, provides guidance for the use of infrared thermography as part of a program for condition monitoring and diagnostics of machines. Thermography can be used to identify and document anomalies for the purpose of condition monitoring of machines. These anomalies are usually caused by such mechanisms as the operation, improper lubrication, misalignment, worn components, or mechanical loading anomalies, for example, are caused. And you can usually see it through a thermographic image as often the first warning that you have that something has gone wrong. It may be something as simple as tolerances that exceed the lubrication tolerance on the bearing, say the ambient temperature is too high. We've seen that. We've seen a lot of other ones. So there's very good reason for these standards and for what those standards are in particular. Lots of thought about. Infrared thermography is based on measuring the distribution of radiant thermal energy, or heat, emitted from a target surface and converting this into a map of radiation intensities, or the thermogram. A thermogram, you'll note, uses artificial colors of the measured surface temperatures in each pixel of the thermogram itself. Okay. The thermographer therefore requires an understanding of heat, of temperature, and various types of heat transfer as essential prerequisites when undertaking an infrared program. If you don't understand the basics of heat transfer or thermodynamics, you're not going to understand where an issue or problem that you see might be coming from, or whether it even is. A motor gives off heat because of its own internal inefficiencies. Every motor is internally inefficient to some degree, so you're not going to understand why, or why it looks hot. So that's why thermographers need training. That's why there's international standards about that training, so people can understand these specific problems if they haven't had enough physics in college. Thermal energy is present with the operation of all machines. It can be in the form of friction or energy loss, as a property of the process media, produced by the actual process itself, or any combination thereof. As a result, temperature can be a key parameter for monitoring the performance of machines and the condition of machines and the diagnostics of machine problems. Newer word is prognostics. That's up and coming, being able to tell how long the machine's going to last in the future from its current condition. So it's a little bit different from other forms of maintenance ideas that have been kicked around. Anyways, back to the text. Infrared thermography is an ideal technology to do this temperature monitoring because it provides a complete thermal images of the machines or a machine component with no physical attachments. That is, you're not taking a temperature directly, because temperature is taken by a thermometer in contact with something, and the vibrational energy of that, or the internal heat of a solid, vibrates, or a liquid vibrates. The thermometer transfers that kinetic energy, and it's measured as heat. Okay, so it's not doing that, it's an apparent heat. You're looking at something, you're looking at the energy that's being given off by this machine, right? Not directly taking the temperature. So there's no physical attachment, so it's non-intrusive. You can do it on machines that are operating because you're not touching it, you're only looking at it, right? It's the apparent energy. This requires a little bit of setup and provides the results in a very short period of time. Another way of doing it, and it has been done this way, is with an infrared thermometer, which takes a spot temperature. So it takes a very small temperature, it takes a spot, but you have to measure this over the entire machine. You can't just decide that you're going to take one spot and you know everything about the machine. In this case, the thermogram itself shows you a large field area, and the relative temperatures all the way around it. So it's a much more efficient, much faster way of taking the temperatures of a very large area and then comparing them, qualitative or quantitatively. Well, this brings us to an important advantage of radiation thermometers over contact thermometers, and it's specifically their speed of response. If you're looking at light, you can measure whatever comes in immediately by the sensors on it, versus a thermometer, which actually has to take that kinetic energy and move something, heat something else up, and you have to wait for it. So a radiation thermometer or a thermogram can do that immediately. If it's again a spot thermometer, you have a small spot. If it's a modern infrared device, it takes a larger picture or presents that picture on the screen immediately. The response of an instrument can be in milliseconds or even microseconds. Another advantage is the sensitivity of the instruments, and they can detect and display the thermal picture composed of a very subtle temperature differences within the target itself. Okay. Although it's extremely useful, IRT has limitations in that radiometric sensing is susceptible to unacceptable error when used on most low emissivity surfaces, and we'll cover emissivity. In brief, emissivity is how much energy is of that heat that conducts to the surface, what percent, expressed as a decimal, will emit from that surface. Kirchhoff's law comes into play, and other rules here. So, the international standard provides an introduction for the application of infrared thermography for the purposes of machinery conditioning monitoring and diagnostics, including machine auxiliaries such as valves, fluid, electrically powered machines, machinery related to heat exchange equipment. In addition, the infrared applications pertain to machinery performance is addressed in the standard. Things like it introduces the terminology of infrared thermography as it pertains to condition monitoring, diagnostics of machines. It describes the types of infrared thermography and procedures and their merit. It provides guidance to establishing severity and assessment criteria for anomalies identified by infrared thermography, and there are different criteria set up there because it's not internationally standardized as of yet. Although I do find that those international standards, the ISO standards that they just suggest in there, are very adequate for calling out most problems. I've seen scales that were higher than that, and potentially problems could have arisen from issues with that different standard. But anyways, so it outlines methods and requirements for carrying out thermography of machines, including safety recommendations. It provides information on data interpretation, assessment criteria, and reporting requirements, and provides procedures for determining compensating for reflective apparent temperatures, emissivity, and attenuating the media. Now, the reason this is important, we'll see in a few slides. Reflective temperature can be higher, can look a lot higher than that. In a minute, we'll look at the desalination device in my geothermal desalination lab. It's on the CSL dock in the back. It's there. You can go look at it if you'd like. And when I did thermographic inspection of that, there's a reflection of me in it, and I look hotter than the device itself, which is at about 98 degrees Celsius, and I look to be a lot hotter than that because of the reflection that comes off the machine. We'll discuss that a little bit. So, the standard also encompasses testing procedures for determining and compensating for reflected apparent temperature, emissivity, and attenuating media when measuring the surface temperature of a target in quantitative thermographic camera. So there's a lot that's covered in these standards. It's a very comprehensive standard, very good standard to read. Well, what terms and definitions are there? Okay, these are things that are defined, and this is taken directly from, much of this text is taken directly from the ISO standard. That's why it'll have numbers incorporated into it. Apparent temperature, the uncompensated reading from an infrared thermal imager containing all radiation incident on the detector regardless of its source. So again, in a minute we'll see one with me, and you'll say, oh, the device is 130, 140 degrees Celsius, and that's not the case at all. It's reflected temperature, and much more of the energy is reflected off of this device because it's made out of 316L stainless than is absorbed by the device. Now, absorbency is the opposite Kirchhoff's law again of emissivity. It's how much hits the surface and how much is absorbed by that surface. It's ob versus reflectivity. It's the opposite number there. So you'll see the reflectivity is quite high, and I look quite hot in that image. We'll see in a second. So attenuating media, windows, filters, the atmosphere, external optics, materials or other media that attenuate the infrared radiation emitted from the source. Cameras attenuate also because you have to be able to turn the scale up and down in order to understand where identify the heat anomaly itself. Often it'll go off the current scale. Everything appears, let's say in this particular rainbow display, as white, and that might be a huge thermal range because the range is limited. So you need to be able to attenuate that. But there's other things that do it. If you're looking through a window, or if there's some kind of a filter, the atmosphere is too thick. Let's say there's fog in the air; it'll absorb a lot of it. Things like this. So, but that's the definition of it. Emissivity is the ratio of a target surface's radiance to that of a black body temperature over the same spectral interval. And the reason the spectral interval is important is that it is the emissivity changes at different spectral intervals. The easiest to figure out is a mirror. A mirror looks like it reflects at least nearly all of its light, but not in the infrared spectrum. When you look at a mirror through an infrared camera, yeah, you can see a reflection, but not nearly as much light is reflected off that. Some of that's absorbed through the mirror. So different ones at different temperatures have different emissivities, different reflectivities, conversely. And okay, the infrared thermographic camera, an instrument that collects, it defines it, of course, as an instrument that collects infrared energy from a target surface and produces an image in monochrome, black and white, or in color. The old ones we used to use 20 years ago were all monochrome. It was all black and white, and it took quite a bit of work to convert those numbers or rather those isotherms really into numbers and determine how much heat was being lost by this device or this surface. Okay, so that relates to the target surface and apparent temperature distribution in the object being imaged. Lastly, on this slide at least, image processing, converting to an image to digital form and further enhancing the image to prepare it for computer or visual analysis. Next term is infrared itself. It is that portion of the electromagnetic continuum extending from the visible red wavelength, or 0.75 micrometers, to 1,000 micrometers in length. Okay, that's the infrared spectrum, and even that's broken into smaller segments. It's near, middle, and far infrared. We're usually looking at far infrared with a thermographer or a thermographic device. An isotherm, enhanced feature applied to the image that marks an interval of equal temperatures. So again, in a black and white photo, you'd see one, let's say pure white, then you'd see a gray area. You might have a line around it according to how that particular camera worked. Okay, it's an isotherm. It means the same isotherm, the same temperature. Okay, so infrared thermography itself is defined as the methodology of analyzing thermal patterns and profiles to detect and evaluate thermal anomalies. Radiation, thermal radiation, is the mode of heat flow that occurs by emission and absorption of electromagnetic radiation propagating at the speed of light, of course. Well, and there I am as promised. Reflected off a piece of 316L stainless steel. You could just about paint this with black paint and get the same image because that black paint would push it into the device and it would reflect back. I've actually seen that happen with dark brown paint in particular. But so rho, Greek rho is the reflectivity, epsilon is the emissivity, and tau the transmissivity. Okay, so the ratio of the total reflected energy from the surface to the total incident energy on that surface. Note that here that is equal to 1 minus the emissivity minus the transmissivity of the material that you're looking at. For a perfect mirror, that reflectivity approaches 1. This isn't a perfect mirror. Reflectivity is probably 0.97, I would estimate, because the emissivity of this device is probably about 0.03 right now, because we textured the device. Otherwise it would have been 0.028, something like that. So technically, reflectivity is the ratio of the intensity of the reflected radiation to the total radiation, and reflectance is the ratio of the reflected flux to the incident flux. Okay, in thermography, the two terms are often used interchangeably. Okay, reflected apparent temperature, again, is what you see. I look a lot hotter at 98 degrees and radiating some of that. I'm a little bit cooler at the skin surface, of course, than the device itself, which is at 98, 99 degrees Celsius. So I look higher. I look hotter, 98 degrees. I'm sorry, I use Fahrenheit on myself, but I look hotter than the device, and I'm simply not. I'm a lot cooler than the device itself, but I look hotter in here because it's additive. It's what you're looking at in my body image area is that heat, which is incident on it from the surface and reflected, in addition to that which is radiated out, and that's why it looks hotter. Okay, transmissivity. What is tau? It's not Tao. For those of you in religious studies, it's tau. Okay, the portion of transmissivity, of infrared radiant energy impinging on the subject's surface for any given spectral interval that is transmitted through the object. So the transmissivity is 1 minus the emissivity minus the reflectivity. Okay, so T is or tau is the transmissivity, emissivity, reflectivity, respectively. Okay, well, what about techniques in thermography? Comparative thermography is the most common technique. It is normally used to provide the best available data in lieu of ideal or absolute thermal measurements. When encountering changing machinery operating conditions, the ability to perform rough emissivity estimates, the ability to differentiate emissivity differences on machinery equipment provides useful information for the condition monitoring and diagnostics of the machine under less than ideal circumstances frequently encountered in the field. In other words, operating conditions, right? So the confidence level of the information is obtained depends on the thermography equipment used, the training and experience of the thermographer, and the detection method applied. Okay? Non-contact thermometry can be done with thermographic equipment. Okay, that's often in a scientific setting how it's used, often with a set camera, very tightly controlled environmental conditions, so those aren't a factor. Okay, this is using thermal cameras used when it is essential to know precisely as possible the true temperature of the target. However, this technique is not normally used for condition monitoring and diagnostics. Again, more scientific level here, because you're going to know the emissivity, and emissivity becomes very critical at that point to knowing what it is. You're usually going to use a fixed camera. You'll find that in several of our labs here, and a very tightly controlled temperature for that environment, so you're getting the same image. You can consistently depend on that data for what you're looking at. Lastly, comparative thermography is normally used as part of a condition monitoring process when such a process is implemented in accordance with ISO 18359. Thermography can also be used, which is of course another standard, ISO standard. Thermography can also be used as a primary or secondary technique for diagnosis and prognosis when these processes are carried out in accordance with ISO 13379 and ISO 13381 respectively. And this is what I was saying a few minutes ago, that prognosis is becoming the new term to be used to tell how long a piece of equipment is going to last into the future, which I really guess means that you are a thermal prophet, telling the future without okay. Moving on. Comparative thermography can be either quantitative or qualitative. The quantitative technique requires the determination of a temperature value to distinguish the severity of a component's condition. Its value is determined by comparing the target's temperature to that of similar surface or equipment from a baseline data. Now, most often this is only done within the same piece of equipment or the same environment or the same within a foot or so. Often, though, a good thermographer will need to go to a different piece of equipment somewhere else, a different surface, to get the ambient temperatures and compare it. That makes it a little bit difficult in some applications, but that's how it's done correctly. Although the temperature value is not precise, it is reasonably close to the actual temperature, and more importantly, the temperature differentials are accurate. Okay, so that's the primary. How much above ambient is this piece versus that? So it's quantitative, not qualitative. We're not measuring the actual temperature. We're looking at the difference between one and the other. So, in addition, many applications also require assigning values to observe thermal patterns for the purposes of analysis, trending, designating severity levels, and assessing priorities for repairs that may need to be needed for future maintenance, preventative maintenance, predictive maintenance, prognostic health maintenance values. Okay. However, there are many applications where quantitative data is not required to monitor the condition of the machinery or to diagnose a problem and recommend appropriate corrective action. In these cases, qualitative techniques are more than adequate. Okay, then there's comparative quantitative thermography, which is the comparative quantitative thermography method is an accepted and effective method for evaluating the condition of a machine or a component by determining the approximate temperatures. In certain cases, the temperature is the critical thing, not the difference in temperatures. It is very difficult to determine precisely the actual temperatures of a component using infrared thermography in the field. This is due to certain extent to the physics of infrared thermography, which must take into consideration the multiple parameters that enable a true absolute temperature measurement. Those infrared thermography considerations are emissivity, reflectivity, and transmissivity. As a result, the estimates of these infrared thermography considerations can be readily made to obtain the component's approximate temperature, and in most cases is more than sufficient to determine the severity of an adverse condition, or in some cases, in scientific senses, the actual temperature of the operating system, because you may have, let's say, a silicon chip that needs to operate within certain temperature ranges, and so determine what kind of airflows you're going to need in the ambient conditions that your device is going to operate in. Okay, back to comparative qualitative thermography. The qualitative measurement compares the thermal pattern or profile of one component to that of an identical or similar component under the same or similar operating conditions. The way this is normally applied is one part of a device to another part of the same device as compared to ambient temperatures. When searching for differential thermal patterns or profiles, an anomaly is identified by the intensity variations between two or more similar objects without assigning temperature values to the patterns. This technique is quick, easy to apply. It does not require any adjustments to the infrared instrument to compensate for atmospheric or environmental conditions or surface emissivities. Although the results of this type of measurement can identify a deficiency, it does not provide a level of severity, so which is applied only by the thermographer himself, comparing that to the standard that they're using. Okay, let's move to non-contact thermometry using infrared thermographic cameras. The determination of correct temperatures of a target using an infrared thermography is very difficult because of many technical and environmental factors involved. As I mentioned earlier, you have to control the environment very carefully. As a result, absolute infrared thermography measurements are done only if very precise temperature values or small temperature differentials are critical to a process. These determinations are normally attempted only under extremely controlled conditions. This type of measurement using infrared thermal cameras is not normally used for condition monitoring. Okay, what is the standard for data collection? Okay, data collection shall be carried out in accordance with the following. 1. Infrared inspections should be performed when the environmental and physical conditions are favorable to gathering accurate data. Sometimes this is critical. These are becoming very popular to use on wind turbines, and in that situation it is critical. You've got to know a lot of different factors, environmental factors. Okay. 2. The operating environmental conditions under which the data is acquired should be repeatable and consistent with normal operating conditions. The thermographer shall ensure that all emissivity and reflected apparent temperature determinations are accurate. 4. The thermographer shall ensure that the target size is within the spatial measurement resolution of the camera itself. 6. The thermographer shall have sufficient knowledge of the design, manufacturing, installation, operation, and maintenance principles of the machine. The typical faults associated with each principle and their resultant thermal anomalies in order to accurately interpret the observed patterns of radiation. 6. The infrared thermographer will use thermography and/or measurement equipment with capabilities sufficient to meet the inspection requirements. And 7. After repair, when the requested by the end user, with the exception, each exception should be re-inspected to ensure that its operating temperature is normal and the potential problems corrected. This is okay. Well, there are certain customer responsibilities. The customer in a thermographic service should, 1, provide or help develop the inventory list of equipment to be inspected in a logical and efficient route through the facility. 2, should provide a qualified assistant or assistants who is knowledgeable of the operation history of the equipment to be inspected when required. This person will accompany the infrared thermographer during the inspection and will be qualified and authorized to A, gain access to the equipment to be inspected, will notify operations personnel of the inspection activities, B, open and/or remove all necessary covers immediately before the inspection by the infrared thermographer, C, close and/or replace those cabinets and enclosure covers immediately after the inspection by the infrared thermographer, D, operate any equipment that is required, if possible, E, ensure that the equipment to be inspected is under adequate load, create satisfactory loads when necessary, and allow sufficient time for the recently energized equipment to produce a stable thermal pattern. Very important. F, measure the electric load when requested by the infrared thermographer. You need to know how the equipment is loaded. If it's half the load, the full temperature is going to be a lot hotter than it would be at half. So you need to know those things. And lastly, take full responsibility, not quite lastly, take full responsibility for the consequences resulting from the actions taken or not taken as a result of the information provided by an infrared inspection. And lastly, provide the information on the results of repair and inspection activities. So the customer himself is responsible for much of what goes on there. The service is okay. The severity of assessment criteria is kind of critical to understanding what's happening to describe to the person the condition of their machinery. Okay. The severity assessment criteria can take two forms. 1, it can be organized into general categories and then identify temperature levels or zones versus level of criticality. Or 2, they can be applied to specific machines or components or to like groups of machines or components. In either case, the levels are established through experience and accumulation of data. In practice, no singular severity assessment criterion is universally applicable to a variety of items existing in the industry. Consequently, severity assessment criteria must be developed for each category of equipment based upon its design, manufacture, operating, installation, maintenance characteristics, and its failure modes and criticality. How critical is this piece of equipment and how much of a load is it under? I found a piece, let's say, on a piece of radar that was under light load at the time, and if it were under heavy load, it would mean we were under severe threat in the United States, and the criteria was moved up quite a bit to make a problem something that needed immediate attention versus a low level because of that factor itself. This is a mission critical piece of equipment, and with heavier load, that hot spot that was identified would have become more critical and possible to fail, and that failure would have been catastrophic to the United States itself, and that's not overstating the issue. And it's I can't exactly tell you what that is. That was a classified piece of equipment, but that leads you to this point: is that severity assessment criteria can be established on individual machines or components. That's what I did in that case, and I told actually the manager of the device, his title was manager, of what we were doing because of this, and we changed the priority because it looked like a low priority issue, but in fact was mission critical equipment. So this method is based on many factors, including the safety of personnel, in this case the safety of the United States, temperature rises versus historical data that establish a rate of deterioration and time to failure. In this case, it was a high-powered piece of it was simply a control panel, but had a lot of electricity flowing through it under certain circumstances, and that would have become critical under those circumstances. So the criticality of the machine or the component to the overall process is important. The location with respect to other materials and equipment, should a fire result, the environmental conditions, etc. So if this piece fails, what will be the result? What else will go wrong? We found a piece that was both the incoming and outgoing control panels for a machine, rather an engine space on a ship that were hot, and if one went, it would have taken out the other one. You would have had a fire in a controlled, small, relatively small space, engine room, on a ship, and you would have had no ventilation. The incoming and outgoing would have taken each other out, and that is one box would have caught fire and burned the other box. So by the time the fire people got there, they would have had no ventilation. That would have been rather important to saving the ship itself. Anyways, so applications could include temperature rises of critical machines, mechanical components, bearing temperature rises, which is the most determining factor in any kind of electric motor, or electrical supply or connection rises in temperature, fluid leakage losses, or even a number of tubes clogged in a fluid heat transfer type of equipment. Okay, so the infrared thermographer may use delta T, the temperature difference, the rise in temperature, the difference in temperature, literally, criteria or classification of the temperature severity of the mechanical system anomalies. These delta T criteria are usually reported as temperature rise of the exception above the temperature of the defined reference. Okay, you open a box, and inside the box is a certain temperature rise, and that indicates a problem. It should be radiating into the environment and be reasonably similar to that, the ambient temperature around it, and it's not. That is the determinant of a problem itself. By taking multiple measurements over the time of similar components under similar operating and environmental conditions, statistical analysis can be used to set operational limits for trending and predicting the temperature performance of these components. A delta T system may be used in conjunction with these absolute temperature criteria to rate the temperature and severity of an exception above the maximum allowable temperature. Okay, temperature difference criteria is presented in the ISO standard, and as I said earlier, we do like this in particular as it is, as the base for most things that we do, at least, that we've been involved with in the past, and for things I train people for. This is it states in the text, this is an example of the severity assessment criteria. I've known people that have used different criteria that are higher temperatures in this, and I disagree with those. I think ISO standard is well thought out, and for good reason. So the categories are advisory, intermediate, serious, and critical, and you can see the temperatures there. Up to 10-degree rise for advisory, 10 to 20 for intermediate. So if you hit 10 degrees, you're at intermediate. So okay, so advisory would be up to 9.99 degrees centigrade. Okay, serious is 20 to 40 degree rise. Anything above that is considered a critical problem, needs to be fixed quickly, needs to be pointed out to the people. So the reference temperature should be based on temperatures specified by manufacturers of similar items or groups of equipment or of components located on the same shaft, say. Baseline temperatures should be based on historical or statistically derived temperatures established from the specific item or machine groups when in an ideal condition, which is usually 14 degrees for most electrical things, 30 degrees for most motors is considered to be ideal, up to 35 on some types, larger equipment. Okay, Fourier's law of heat conduction. Look at the motor design and think about what's going on inside that and how you get heat from the inside to the outside. Realizing the purple rotor in this image, there's an air gap between that and the stators on the outside, and there's air gaps here and there. Okay, Fourier states that the energy rate through a solid material, say a rotor shell or a housing, equals the thermal conductivity times the difference in the temperature between the inside surface of the motor casing and the outside surface of the motor casing, multiplied by the area of the casing and divided by the thickness of the casing. Okay, so it's a little bit complex, but you're looking at this motor that shows some heat, and unfortunately there is no easy way to tell what the internal temperature is when you have found the outside temperature. Since an electric motor, the rotor may have a slightly higher or a much higher temperature than the stator. There's an air gap between them. The gap will insulate the rotor, causing the rotor to heat to radiate, then convex and radiates to the housing. The second law demands inefficiency at each step, and Kirchhoff does as well, and so causes a low heat transfer from the rotor to the air gap, then to the stator, and the stator partly to another air gap, partly via conduction to the casing. So there's a lot of entropy going on at each step, which is okay in this process, but the internal heat of the motor builds up. So many things go on inside the motor, and many designs of motors are available. You can't give the internal temperature based on the knowledge of the outside temperature. If you're lucky to find an open motor design, you may see temperatures of the stator coils up to 150 degrees C, and not much of an increase on the outside of the motor casing. If the motor has a fan on the non-drive end, as this one does, there will be outside forced convective cooling, which will increase the heat transfer to the surface of the motor casing, which will then give you a lower temperature on the outside, while the inside is still quite hot. But at least you're getting rid of it. That's what you want, the thermal conductivity out and to remove it. I've seen motors where the fan has been blocked and the motor is running at, let's say, 100 degrees C, only to run nice and cold at say, 20 degrees rise above ambient once the block has been removed. Unfortunately, thermography isn't the final analysis tool that we had hoped for in these cases, but with trending, you'll be able to find something that is getting worse. You can watch it over time increase the problem. The temperature will increase. If you're going to adequately diagnose a machine using thermal imaging, a low rated criteria is important for these reasons. Okay, back to the ISO standard, which describes a maximum allowable temperature criteria The infrared thermographer may use an absolute maximum allowable temperature criteria based on published data to identify mechanical system anomalies. It must be well understood that there are two categories of criteria, those being material and design. Material criteria are used when the integrity of the material itself is of concern and the focus of the monitoring. Let's say it's a wall, a piece of metal, a printed circuit board, some lead or non-lead soldering, whatever it may be. That's a material condition. The lubrication in a motor bearing. Okay, a design criteria used when the design integrity is the major concern with the focus of the monitoring. Design criteria should always be used in preference to material criteria, as design criteria normally incorporate material requirements. So the design we saw a second ago, this very detailed motor, the main issue is going to be the temperature of the bearing lubricant. That's going to be the most important. So it is a material criteria, but it's the design of the motor that makes that requirement so critical. So design criteria are usually cognizant of the performance, operation, and reliability and capacity criteria other than just the component material integrity. When an exception is heating of several adjacent system components and a material criteria is used, the component material having the lowest temperature specification should be the reference as the alarm criteria. So this is the weakest link in the chain type of an argument there. I would refer you again to the previous diagram to understand why the design is the proper criteria in most cases. Okay, again though, in most machines the lubricant will have the lowest temperature specification. For some reason grease has a lower tolerance to heat than metal. Go figure. Okay, so it's all obviously related to the chemical constituents that make up each, and metal can take a lot more heat and lose a lot more heat than can, let's say, grease or the lubricant, whatever that is. Okay, the maximum allowable temperature should be stated as the temperature above which an unacceptable loss of component life will be experienced due to a loss of lubricant characteristics. Such reduction in characteristics may be immediate, such as viscosity, or long-term, that is additive depletion. You heat it up a little bit, you're going to get additive depletion. You heat it up a lot, your viscosity is gone. Your bearings are going to fail, and that's 85% of all motor failures are bearing failures, and that's because the lubricant, there's something wrong with the lubricant. It gets too hot, or you didn't change it, it just wore out. Okay. Such a criteria will tend to be design rather than materially based. They will require application of specific temperature criteria despite the possible use of common lubricants. And lastly, as we close this session, we have another to do on the other aspects of the ISO standard. But realize the reason that is for the lubricant is that the bearings themselves are the ones taking the friction. The lubricant is trying to reduce that friction, of course. But the bearing themselves may be 10, 15, maybe 20 degrees higher than the temperature of the grease, and or the apparent temperature of the bearing on the outside. You're looking at the outside of a casing. Again, go through that process. You have a bearing getting hot. It's heating up a lubricant, an oil, which doesn't conduct very well. Okay, foyer again, and then that has to conduct out to the surface of the housing itself, and then you have, then the motor itself is painted, let's say gray, and it has a certain emissivity. So the bearings themselves are going to be a lot hotter. So that's why the ISO standards are important. That's why we think they're critical to use those as they are and then adjust them as needed.